trying to figure out like if two atoms are the same on a chiral center. You got to be able to use that skill. So are they the same? Let's see. So these two are both carbons. Uh-oh. Sorry about that. They're both carbons, is that right?
Yes.
Right.
So if we go to this card, so they both with both those being carbons, they're identical, or at least they look identical, but we have to keep going. So if we look at this atom and this atom, is there a point of difference?
Yes.
Yes.
Yeah, there is, right? This atom over here has a hydroxyl group attached to it, and this atom doesn't. It's bonded to nitrogen.
Right.
Right.
So those are different. So that's how you can tell your groups apart.
Okay.
Are y'all following that?
Yes.
Is anybody not following? Because don't get lost now. I got a couple of life jackets I could throw out. Fall off the boat. Don't fall off the boat.
I'm trying to stay on the boat.
Stay on the boat. Are we okay with that?
Yes.
So where are our chiral centers? We're going to leave the nitrogens out because that's a sometimes, right? Sometimes it'll be chiral, sometimes it's not, depending on, you know, certain other circumstances, right? But we know for a fact that we got chiral centers here and here. Is that right?
Yes.
Yeah, so for a chiral center, it doesn't have to be carbon.
No, it can be other. Sulfur can be chiral. Silicon can be chiral. It just has to meet those criteria. Non-superimposable mirror images, 4 different groups, sp3 hybridized and non-symmetrical. If the atom meets those 4, then it's going to be chiral, or it's going to be a chiral center. Is that okay?
Mm-hmm.
All right. So now,
Yeah.
I see a chat. Hold on. Okay, never mind. All right, let me erase this and let's talk about another concept. And you already kind of saw it already in the video. It's talking about configuration. But before we get to that, I want to talk about one other thing before we talk about configuration. And are we all on the same page? I'm not going too fast, am I?
No.
No.
Okay, great.
Nope, follow me.
So let's do this. Let me give you a piece, another little nugget to hold on to, and then we're going to apply that to some other examples as we move on, right? So let's say, for instance, in Lipitor, we've identified 2 chiral centers, right? We're not going to count the nitrogens, okay?
Yes.
So now the question is, how many? And this is a question that every synthetic chemist has to grapple with when they're making stuff like this. How many total stereoisomers are possible? Sorry about that.
Can you define stereoisomers one more time?
So a stereoisomer is a molecule, two or more molecules that have the same molecular formula, but they have a different 3D orientation.
Okay.
So a pair of enantiomers, those would be considered stereoisomers. All right, are we okay?
Yes.
All right, so now the question is, how many total stereoisomers are possible? And there's a way to find that out, right? The way you determine it is to find the number of chiral centers. And so we're going to say that the N is the number of chiral centers, right? We're going to use that just a random term. We're going to call it N. The way you figure out how many stereoisomers are possible is 2 to the N. I'm going to abbreviate that so I don't have much space. Number of possible stereoisomers. That's not a hashtag. Are we okay on that?
So N equals number of chiral centers.
Mm-hmm. And 2 to the N will tell you how many stereoisomers are possible. Yes, no.
What was it again?
Say again.
The number of chiral centers.
Mhm.
And once we identify the number of chiral centers, it'll give us the number of stereoisomers.
Yeah, we can find out how many stereoisomers are possible. Yes.
Right. So if it was 2 of them, 2 to the second power, we'll have 4.
Right. So for this molecule, 2 to the 2 would be 4 possible stereoisomers. That's exactly right.
All right.
Okay. What does that mean for me if I work for Merck or Bristol Myers or Amgen, right? And I'm in the lab. What does that mean for me when I'm making Lipitor for a living? And I got 4 possible stereoisomers that I can have, but I only need 1. And if I give you any of the other 3, it might kill you. Are you following? Because it might not bind to the receptor the right way, or it might bind to the wrong receptor. Does that make sense?
I think so. It's like you're finding different possibilities.
Right. You know that these other possibilities exist, but you only need this one specific one. That's why you see this molecule and not the other 3, because this is the one that works.
Oh, okay.
Are you following?
Yeah.
So what would the other 3 look like? Let's think about it.
Oh Lord.
It's not an oh Lord. I promise. It's not an oh Lord. It's very simple.
Question.
All right. Tell me what one of the other 3 would be, right off the top of your head, that we've already learned.
Glucose? I don't know.
Huh?
Glucose? I don't know.
Glucose. Where that came from?
Wait, I thought you were asking what kind of.
No, I'm asking. Okay, so this molecule has 2 chiral centers. Yes. We all agree on that.
Mm-hmm.
Uh-oh.
Yes.
Life jackets out.
Yes.
So we all agree there's 2 chiral centers. Yes.
Yes.
We all agree that if it has 2 chiral centers, and if I take that number and put it into this little formula over here, 2 to the n, that means I'm going to get 4. I have a possibility of 4 different stereoisomers.
Yes.
Yes.
We're all on the same boat. This one was shown here is only one of the 4. Are you following?
Right.
Mm-hmm.
So what does the other one, what's the other one? What's one of the other 3 that's left? We already.
2 of the OHs, one will be a dash and one will be a wedge.
Okay, I'll take that. But that's not that's what I'm looking for though, is that wouldn't this have a mirror image?
Yes.
It would, wouldn't it?
Yes.
So
Yes.
the mirror image of this, that's another stereoisomer, is that right?
Mm-hmm.
Yes.
What is it called if it's the mirror image and it's not superimposable?
Enantiomer.
Enantiomers.
The enantiomer. So the enantiomer is another stereoisomer. Are you following?
Yes.
Yes.
So that's 2 out of 4. Yes.
Mm-hmm.
This one plus the mirror image, that's 2 stereoisomers. I got 2 more that I can make. Are you following?
Right.
Right.
All right. So now let's talk about that. We okay?
It's dia.
Everybody feeling all right? Y'all need some tea?
Oh.
I got some ginger in the bottom of here.
I think if you read.
It's not spiked though. Not today. It's just the first day,
Oh.
first week of school, so no spiking yet. When y'all start stressing me out, I'll spike it. Okay. So let's talk about the other 2. Are we okay so far?
Mm-hmm.
Yes.
Don't worry about it. If you don't get a chance to write everything, this will be uploaded to YouTube. You can rewind it, pause it as many times you need to. All right. So let me just, because all of this stuff back here is going to be the same, right? So I'm not going to redraw that. I'm going to redraw this part.
Mm-hmm.
Okay.
All right. So
So when you said that they will have like a mirror image or something, it would just be this side with the chiral center.
Yeah. Because nothing else is chiral, right?
Yeah. Okay.
Right. When we said we're going to exclude the nitrogens, because that lone pair can switch up. So it's always going to be going back and forth. Are we okay with that?
Yes.
Would the mirror image look like that? Where both of those are different
Yes.
and both reversed?
Mm-hmm.
Are you following?
Yes.
Yeah. So I could draw it that way, or I don't want to confuse you, but I'm gonna draw it another way too, just so you can understand. I could put a sloppy. Sorry. I can put a mirror plane here and
Right.
draw it this way, where it's looking at itself, right?
Right.
And then the OH
Okay.
is here,
Mm-hmm.
and it's still wedged, and then the other OH will be here, like that. I can draw it either way.
Yeah, I got that.
They're both going to be the mirror.
Oh, okay. Okay.
You follow me?
Yes.
Yes.
One way to depict the mirror image is to draw it like you see it, right? Put a mirror plane here between one side and then draw the mirror image on the other side. But you can't change the stereo centers. You got to keep them, it's got to look identical so that when you flip it, they change, right? Which is what this would be. This is that mirror image flipped over. You see the difference in the wedges becoming dashes?
Yes.
Yes.
Right.
Ginger, sorry.
Okay.
All right, are we okay?
Yes.
So that's the mirror image. So I got 2 of my 4 stereoisomers knocked out. The other 2 are not going to be enantiomers like the original. All right, I'm gonna. Can I erase this part? Which one can I erase? The red
Just
one?
the red one.
All right, I'm gonna erase the red one. Now we're gonna talk about these other 2 stereoisomers. So I could also, somebody already said it too, and I'm glad. Make sure I got enough carbon. I'm gonna do this. I'm gonna take this one and leave it wedged. And then I'm gonna change the other one and make it dashed. Do you see that?
Yes.
Yes.
This image is what we call a diastereomer. It's not an enantiomer. Right? It's a diastereomer. Yes or no?
Yes.
Yes.
It's a diastereomer. It is not a mirror image, but it still contains 2 chiral centers. Are you following? So it's not a mirror image, but it still contains 2 chiral. It still contains chiral centers, even though it's not the mirror image of the original image.
Mm-hmm.
Right? So the way you draw the diastereomer is to alter 1 stereo center and keep everything else the same. Even if you had 100 stereo centers, a diastereomer is going to be altering 1 of those at a time. So the diastereomer is not a mirror image at all, right? But it's still chiral. And in order to have diastereomers, you need 2 or more stereo centers.
Wait, say that again.
In order to make diastereomers, you need
Right.
2 or more stereo centers.
Oh, okay.
Right? 2 or more chiral centers. So you see how right here we got 2 chiral centers, right? So that means we got 4 stereoisomers. If I only had 1 chiral center, 2 to the end would just be 2, wouldn't it?
Yeah.
So so I would just have 2 stereoisomers, which would be the original and the mirror image. But the minute I add in more chiral centers, then I introduce the potential for more stereoisomers.
Mic is on like that.
Does that make sense?
Mm-hmm.
All right, so what is the other diastereomer going to look like?
What's that noise?
It's
It'll
gonna be the
same,
opposite.
It might breathe.
One will be wedged, and
It
the
might
other
fall
one will be.
asleep.
Well, okay, there we go.
Say that again.
The first OH will be a wedge, and then the second will be dashed.
So we're going to change. We're going to change the other OH. Is that right? So we're going to make this dashed, and we're going to make this one wedged. That dash is bad. Let me fix that. Yes?
Yes.
Mm-hmm. So those are your other two stereoisomers. So now, do you see how we have a total of 4? We have the mirror image, and then we have 2 diastereomers. Are you following?
Mm-hmm.
Yes.
Now, I will cash app you lunch money. The first person to tell me what the relationship is between the 2 diastereomers.
Hold on.
Their mirror images.
Who said that?
Natalie.
Natalie trying to get that lunch. Natalie, put your cash app in the chat box. You're right. They are mirror images. What I need y'all to understand is when we talk about mirror images, a mirror image is the reverse of the original image. Are you following? It's the exact opposite. So do you see how up here on this top image, how the OH is wedged and the other one is dashed? And in the bottom image, it's the exact opposite.
Yes.
Yeah, so these two, although they are diastereomers of the original image, when you compare them to each other, they are enantiomers. You following? Or no?
Yes.
Yeah, so they're mirror images of each other, but when you compare them to the original image, which is this image right here that we started with, they are diastereomers of that image or that molecule. Yes or no?
No, yes.
Mm-hmm.
All right, so now we're gonna stop because it's 10:25. And I'm open the floor up for questions. All right, Natalie. And look, y'all see I'm a man of my word. I'm about to cash up her right now.
I see.
I keep my word, and that'll keep it interesting because I do that a lot. So if you want some free lunch, you're gonna have to study and answer some questions. Let's see.
Wait, one question. What is it? What diastereometers do they the same chemical compound? Like they will produce the same thing, or are they completely different molecules?
They're totally different, and they got different physical properties too.
Okay.
So that's a good question. So remember when we were talking about making this drug, right? So when you make the drug, there's a couple of ways to go about it. One way is to make it using some type of process that only gives you that stereoisomer that you need and excludes all the rest of it, right? We're gonna talk about that Monday, as a matter of fact. So you can make it and then you exclude out the rest. It's called, you can do what's called asymmetric catalysis, where you make specific enantiomers and you don't have to worry about the rest. Another thing you could do is separate them out. So let's say you make all 4, there's a way to separate them out. The good thing about diastereomers is that they're physically different. So you can separate those physically. When you got 2 enantiomers, it's not so trivial to separate them, but you can't get them separated. That's a great question. But the diastereomer is gonna have different melting points, different RF values. If you're doing TLC, like chromatography, all of that's gonna be different. And that's what makes it so easy to separate.